Now let's look at the decay width of unstable particles. Now we can, our previous formalism of the scattering cross-section, let's remember the expression of the scattering cross-section we have. This is the normalization and the flux of the initial particles. Then we have the phase space of the final state particles. We have the energy momentum conserving Dirac delta. And then we have the transition probability, where if you remember, we had defined this transition probability through the S matrix element or the T matrix element. These are the ingoing states, these are the outgoing states. This we had defined as 2 pi I t. We said that we are not looking at the processes. Well, in fact, this is just S for Ka, Kb going into Kf. And this we had defined as the identity, no transition, plus It. If we are looking at the non-trivial processes actual scattering, this will be 0. And this matrix element, the T matrix element, we had defined, since there will be an overall energy momentum conservation, 2 pi to the 4 Dirac delta, Ka plus Kb minus Kf. What remains is our invariant matrix element. This is our definition of the invariance matrix element. Now let's look at this d sigma, and let's see how we should modify this if we are looking at processes in which, for example, we have an initial particle, it decays into some final state particles. Now, first of all, to start with, here we won't have a flux of collisions. We would just have a single normalization of this, the initial particle, this unstable particle. This term will be there. We will not have this EB term or VA minus VB term. The final state, we need to sum over all the final state particles. This phase space factor will still be there. The energy momentum conservation will still be there, the overall for energy momentum conservation. And also the corresponding T matrix element. Of course, this time it won't be the T matrix element of such a scattering, but the T matrix element of decay. So the gamma decay width. Remember, this cross section was kind of the number of the scattering probability, and the gamma is the decay probability. And the gamma is defined in the rest frame of the initial particle, so that here the normalization of the initial particle at rest would be just 1 over 2m. And we will have the final ma, the sum over the final state phase space. Then we have the energy momentum conserving Dirac delta. And finally the invariant matrix element. Now let's forget this I m squared. This will be the width of the particle. Well, this is the width corresponding to the decay Ka goes to K1 up to Kn. Now, if the particle is can decay, let's just call this d gamma I. If the particle can decay in more than one way, the total width, the total probability of the particle to decay to an arbitrary final state would be just the sum of all possible final states, let's say F, over all final states F. And remember that this gamma actually arises in the definition of the rate of change of the number of particles, a particles as a function of time. This is defined as minus gamma times NA. So essentially, gamma is a measure of the probability per unit time that there will be the A particle will decay. So with this identification, we can also calculate the decay widths of particles once we determine how we can calculate this invariant matrix element. But note that in the case of these decaying particles, we cannot actually define this Ka in state. They are not well defined because remember these in states are defined at time t is equal to minus t, which goes to minus infinity. But for unstable particles, if we have unstable particles at minus infinity, at now they have just all decayed. None of them exist. Well, this expression, although for the time being there are some sort of formal difficulties in interpreting this expression, we will see in our future discussions how we can actually define the width of unstable particles, and there we will see that this is actually the correct expression for the width differential decay width of unstable particles.